Hello and welcome. We present RehabGen. The goal of RehabGen is to tackle current AI rehab constraints, which is low motivation, unclear goals, and difficulty incorporating exercises. We aim to turn daily environments into therapeutic opportunities using household items and home activities for rehab plannings. RehabGen transforms multimodal data into personalized exercise recommendations for better real-world adaptation. The system begins with multimodal inputs. These are then processed with a vision language model, which is fine-tuned by expert preference data. And model inferences personalized rehabilitation plans. Now let's walk through how RehabGen was built and tested out. We began with expert interviews with 3 experts who have over 20 years of experiences. They emphasized the importance of home rehab using familiar objects and rehab diversity. In a focus group interview with 4 additional experts, we extracted 6 core components for contextual rehab planning. Our pipeline begins with an egocentric image of the patient's environment. A vision language model infers symptoms and key objects which guide retrieval of clinical context from a PDF-based reg model. The retrieved knowledge forms a context prompt combined with SOAP and structure prompt. The final output is a JSON containing 6 key components. It is later used as an initial rehab dataset. Then we ran the expert in the loop collection. 7 experts from PT/OT participated. They reviewed the patient's metadata and egocentric images to understand the environment, then provided their preference on generative exercises. They also leave their custom label by clicking Need Revision button. Using our expert in the loop interface, experts provide their feedback by dragging start and end points and writing their own custom labels. This preference enabled direct fine-tuning of the model. We applied 2 different methodologies for fine-tuning, and the DPO strategy better reflected expert values in terms of the reward margin. We also ran a user study with experienced rehabilitation professionals. We recruited 23 participants with average 7.5 years of experience. They compared the outputs from 3 different models, which is baseline, SFT plus DPO, and DPO models. A follow-up post-survey evaluated 6 dimensions. In expert validation, the DPO model achieved the highest item level win rate of 57.6%, which is outperforming the baseline. Across 6 criteria such as personalized recommendation, identify purpose, and recommendation satisfaction, DPO shows the higher performance over baseline, while SFT DPO showed the higher performance, especially in conciseness. Likert scale ratings further indicate higher satisfaction with DPO outputs, especially in identify purpose and recommendation satisfaction. We additionally recruited 8 participants who has diverse upper limb conditions and rehabilitation goals. In this patient's experience evaluation, our DPO and SFT DPO model shows higher preference win rate over baseline. This example illustrates that DPO model generated the most clinically relevant and context-aware recommendations by incorporating patients' actual impairment, measured grip strength, and environmental context. Qualitative reflections from patients' group highlight that SFT DPO improves contextual grounding, DPO enhances clinical realism, while baseline still lack fit to environment. As contributions, we define a generative contextualized rehabilitation design framework. We also construct an expert-aligned multimodal training data and fine-tuning pipeline. We validate the effectiveness of expert-in-the-loop generative planning, and finally, we release our fine-tuned models as open source.